Okay, so how does this apply to forces and equilibrium in space? Okay, so according to our definition earlier, we already know that some of the forces in the x direction, some of the forces in the y direction have to equal zero when they're in equilibrium. Same thing for the z. Still needs to be some of the forces in the z direction need to equal zero. So we can use these conditions to help solve problems dealing with the equilibrium of a particle involving no more than three unknowns in forces in space. So in other words, x, y, and z. So the first step in solving these three-dimensional equilibrium problems is to draw a free body diagram showing the particle in equilibrium and all the forces that are acting on that particle. What then we can do is we can write equations of equilibrium and we can solve for the three unknowns using one of the methods we learned in chapter 1. Okay, so that addition or subtraction of equations, Cramer's rule that we used, or a reduced row echelon form, that RREF matrix that we learned last chapter. And you can pick any of these. Any of these will work. Okay, so let's see how this is all going to work. We are going to look at sample problem 2.9. In your book, it is on page 61. And let's go back to our black pen. Okay, so really all this is, it's a barrel or a cylinder that has a mass of 200 kilograms, and it is hung by a means of two cables, AB and AC, that are attached to the top of a vertical wall. A horizontal force P that is perpendicular to the wall holds the cylinder in the position that is shown. We want to determine the magnitude of P and the tension in each cable. Okay, so A is going to have four forces acting on it. Okay, so let's just kind of start with our free body diagram here. Let's draw our x, y, and z axes. There's our x and y, and z is coming out this way. When I get into more complicated problems, I'll label these a lot more. Okay, so our 200 kilogram cylinder is hung by a means of our two cables A, B, and AC. Now, wouldn't it be nice if they just put everything in a... So one thing you can do is notice how in the picture it doesn't show it at 0, 0, 0. I really could put that at 0, 0, 0, but it might make things a little bit more complicated because then I have to do some more math. So what I'm going to do is I'm just going to say everything meets here at point A. That's where all the forces are going to meet. Let's put that down a little farther because let's put it, we'll put it right here. Okay, so if I look at where point A is on my drawing, on the picture that's shown, it looks like it's 1.2 meters along the x-axis. Oh, not 5. 1.2 meters. And it looks like it's 2 meters up. And it looks like it's lying right on that XY plane. So it has a coordinate of 0 for the Z. Okay, so that's where point A is. Okay, just so we know where it is at. Okay, so now what I'm going to do is I'm going to draw everything that's acting on it. Okay, so it looks like I've got first a weight. It's going to be acting downward. I'm going to have to calculate that. P is heading off perpendicular to that wall. The wall looks like it's on the on the YZ plane. So that means it's just going to follow the x-axis here. That's going to be force P. Let's make that a better P. How about that? That's kind of better. Okay, then I have a cable that's supporting it from A to point B. So it's going to go cut off kind of like this. Oops. Let's try that line again here. I was too close to the edge of my tablet. Okay, so here's point B. Okay, and point B, I'm going to take a look at it. Looks like it's 0 in the X. Looks like to go up to it, looks like 12 meters up. And forward 8 meters along the Z. That's the coordinates for B. Okay, and then C is back here. I got another cable, right, at point C. So I've got another force acting there. So notice all of these are pulling away. Those are in tension. Okay, so it looks like point C, if I look at my drawing here, looks like it is also 0 in the X. In the Y, it's going up, same amount. Okay, it defines the wall as 12 meters high. And that Z coordinate looks like it goes 10 back along that wall. So we will do a negative 10. Okay, so there are our vectors. These are all going to be in equilibrium, all of them. Okay, so all that means is that all the sum of all the forces in the X direction have to equal 0. The sum of the forces in the Y have to equal 0. And the sum of the forces in the Z direction have to equal 0. So what I'm going to do is I'm going to define a unit vector for all of these. And that then will help me figure out how big P has to be. Okay, so I'm just going to start by putting two of the easiest vectors in Cartesian vector notation. So P is easy. P is just going in the I direction. Okay, so I'm just going to say P, the vector P, is equal to the magnitude of P times the unit vector I hat. Okay, I'm going to do the same thing for the weight. Weight's a vector, and it's just going, oh my goodness, it's just going in the Y, the negative Y direction, and it's a negative mass times gravity J hat, and not I hat. We are looking at J hat here. Okay, so that is going to equal, okay, the mass of that barrel was 200 kilograms, so I'm going to have a negative 200 kilograms times 9.8 meters per second squared. Okay, so that means W here, the weight, is going to equal 1,000 and negative 1,962 newtons J hat. Okay, just going in the J hat direction. Okay, well, we still have a few to define. Okay, so we've got the tension in cable AB. So let's call this T AB. Oh gosh, that looks like a D. And let's call this one T A C. Okay, so we want to find a unit vector for TAB. And we can find it because we know what the 2 points are. We know what point A is and we know what point B is. Okay, so let's call this one. I'm going to kind of separate these. I'm going to just do this. T. All the stuff for TAB I'm going to put right here. Okay, so D sub x for TAB. Okay, it's going to be from where I end minus where I start. So this is going to be 0 minus 1.2. Okay, so that means D sub x is going to be 1.2. Okay, D sub y then is going to be from where I end. So 12 minus 2. That's going to be 10. Okay, and then I've got D, oh yeah. Try that D again. D sub z, okay, is going to 8 minus 0. Well, that's easy enough. Okay, there are my 3 components. So now if I figure out the magnitude of D, that's just the, so we'll call this DAB. Okay, that's going to equal the square root of 1.2 squared plus 10 squared plus 8 squared. So that means DAB is going to equal 12.86. Okay, so to find my unit vector, my lambda for AB, my directional unit vector, okay, is going to be dx divided by dab. Okay, so this is going to be 1.2 divided by 12.86 I hat. Okay, so that means then for y, I've got a positive 10, so we'll do plus 10 divided by 12.86 j hat plus, and then I need the z part, that's 8 divided by 10 k hat. Okay, so that means the unit vector for AB, okay, is going to be okay, so the I hat is going, oopsie, 0.0933 I hat plus 0.778 j hat plus, that's going to be 0.8 . Okay, that's the direction vector, right? Or that's the unit vector along that line of action for that force TAB. Okay, so what that's going to help us with is so when I write TAB, right, I can write it like this. TAB, okay, it's going to equal 0.933